Everyone, welcome to our very first lesson in our second unit, Physics 30. We're going to be looking at Unit 2, which is Forces and Work. Just talk about some of the outcomes that we're going to be achieving in this unit. The first one that we're actually going to look at is actually one that we looked at in our first unit, where we're looking at 1- and 2-dimensional uniform motion. Specifically in this unit, though, we're going to look at the circular motion, whereas last unit we looked at uniform motion in terms of speed and velocity. We looked at acceleration, and we also looked at projectile motion. So specifically, we're going to be looking, beginning with some circular motion there. Number 2 is we're going to analyze the effects of of forces on objects undergoing uniform motion, acceleration, and circular motion. And number 3, we're going to look at the nature of mechanical energy and efficiency in mechanical systems in relation to the law of conservation of energy. So in our first lesson here, we're going to be looking at the 4 different types of forces. And when we're talking about the 4 different types of forces, we're not talking about, the force in Star Wars. We're talking about the force that you can apply on objects. Say, for example, when you drop an apple, there's the force that's pulling that apple to the ground and that causes it to hit the floor. So what we have to talk about first off is Newton's laws of motion. So Newton's laws of motion explain the relationship between acceleration and its cause, which is force. So just as a general definition and kind of some description of what force is. So first of all, force, it is a vector quantity, and we denote it with a capital F with an arrow over it. Remember that arrow indicates a vector quantity, which, if you guys remember from our first unit, a vector quantity means that it has a direction as well as a magnitude or a size. So force is a push or a pull. It may cause the object to change its shape. It may cause the object to accelerate. It will not change the object in any other way than its shape. And it is a vector quantity. So we have 2 different units for force. The first one here is that it is in kilograms times meters per second squared. Or one thing that we can simplify kilograms times meters per second squared is simply just a Newton, which we can let be a capital N. So one thing that's interesting about our first way of showing the units for force is that this actually talks about what our equation is for force. So here we're looking at kilograms, which we typically know as our mass, and then we have meters per second squared, which we know from our first unit is a way to represent acceleration. We're actually going to write down that equation a little bit later on, so don't worry just yet. So just to kind of talk about what 1 Newton even really represents. So if we were to look at, say, a 1 kilogram mass object, 1 Newton would be the amount of force required to move that object with an acceleration of 1 meter per second squared. And here, when we're talking about, say, something like gravity, the direction there would be down. But we are going to look at 4 different types of force, and that will depend on or decide the direction that we're working with. Okay. So the first one that we're going to look at is called the applied force. We denote that with a capital F with a bracket or arrow over it, and then a little a at the bottom here. So this is saying that this is our applied force. Okay. So when you think about what applied force is, the name really itself speaks for it. It's the force that you're applying to an object. So say, for example, maybe you're pushing a wheelbarrow just like Shelly is in here. So Shelly is applying force to get that wheelbarrow moving. Looking at our second type of force, this one here is probably the most common type of force that we know, and that is the force of gravity. That one we denote as a capital F with an arrow over it. with a subscript G, G standing for gravity. This one here is also called your gravitational force. So this one here is the force which the Earth, Moon, and other massive bodies attract an object toward itself. So an example here, which might be, a little bit less common than, say, gravity keeping us humans here on Earth rather than floating out in space, is even just look at the gravitational force of the sun on the Earth, and it's holding Earth in its orbit. Okay. So on Earth, all objects experience a downward force of gravity. So if you guys were to hold, say, an object, maybe like an apple, you're holding it out and you drop it, it's going to fall downward, and that's because of the gravity on Earth. So the gravity, the force of gravity on an object is always equal to the weight of the object. And so this one here is really important, is that we're talking about the weight of an object. So we're looking at how much force is being, is it being applied to that object. And so this one here is a bit of a new term in terms of physics. So far we've really talked about what mass is, but we haven't really talked about what weight is. Some people might commonly think of it as, weight and mass being the same thing, but they're actually two different definitions. So weight is actually the force of gravity acting on an object. So your weight could be different, say, on Earth, and say if you were to go to the moon, or maybe you went to Mars. How much you would weigh would be different on each planet or each astronomical body. Mass, on the other hand, is, if you guys remember back to grade 9, grade 10 science, is the amount of matter contained by an object. So no matter where you are, whether it's on Earth, Mars, Moon, maybe Jupiter, your mass will always stay the same, but your weight would be different because your weight is dependent on the force from that astronomical body. Okay. So let's get into the equation for our force. So our force, which we're just going to denote as F with an arrow over it, is equal to your mass times your acceleration. And in this case here, we're going to use the vector quantity for acceleration, just because we need to introduce that direction in there. So this is also how you calculate how much you weigh. So you would take your amount of mass and you would times it by your acceleration. So if we want to specifically look at the force of gravity, we can simply just change our acceleration to just being the letter G, because we know that letter G stands for gravity. So force is equal to your mass times your gravity. And this is actually one of the formulas you will find on your departmental formula sheet. So first, going to write down what each of our variables here means. So our F with a capital, our capital F with an arrow over it is equal to your force. M stands for your mass. And if you guys remember back to what we had said on the previous page about our units for force, is that this here should be in kilograms. And then our acceleration, or the gravity, that one there should be, so I guess we can say that'll be in gravity. And then your units should be in meters per second squared. And then if we're talking about direction, it should be down. So far we've talked about two types of forces. We have our applied force, which is the force that, say, you would be pushing onto an object, or you have your force of gravity, which is the gravitational pull from some sort of large body, say like Earth. So the next one that we're going to be talking about is called your normal force. That one is going to be a capital F with a subscript N. So normal force can also be called the support force. It is exerted on an object which is in contact with another stable object. So on a level surface, the normal force is equal to the magnitude, but it's opposite in direction of the force of gravity. Okay, so this one here is really important. So it's equal to in magnitude, but opposite in direction from that force of gravity. So this is the opposite, essentially, of your force of gravity. So one thing that's going to be really important is that if you have a stationary object, like it's not moving up or down, then that means that your normal force and your gravitational force are the exact same. If one were to be higher than the other, then that would cause your object to move up or down. So say, for example, we're looking at, say, maybe a helium balloon. There would be some gravitational force acting upon that balloon, but we know that that normal force that's helped pushing up that object, we know that that one there has to have a greater value, because you know that helium balloons will rise up. And if there's no surface like a roof or a ceiling to stop it, it's going to keep going up into the atmosphere. So also say, for example, if you guys were to put, maybe you got a can of Coke and you put it on top of your table and it isn't moving anywhere, then that means that normal force and the gravitational force is equal. If it's maybe if the force of gravity was greater, maybe it's going to, what would happen is that it would break your table and your can of Coke would go through it and hit the ground. Okay, so that one there is that opposite force from the gravity, and assuming that you have an object that isn't moving up or down, then you would assume that the normal force and the force of gravity is equal. Okay, so the last one that we're going to talk about is the friction force. We also call it your frictional force. So this one we denote as a capital F with an arrow and a little f as a subscript. So this is the force exerted by a surface as an object moves across it, which we call the sliding friction. Or makes an effort to move across it, which is your static friction. So this force is opposite to the motion of the object. So it's actually opposite to your applied force. So your applied force would be going forward, and this frictional force is pushing it back, which is how you get that resistance with different objects. So the force of friction is equal in magnitude, but opposite in direction to the applied force. So it's opposite in direction to the applied force, but same size, assuming we have some sort of stationary object. Once again, if say your frictional force was stronger than your, or higher than your applied force, then that object isn't going anywhere because there's too much resistance to it. Whereas if your applied force, if you're pushing it harder, or I guess with more force than say the frictional force is, resisting it, then you're going to be able to move that object. So friction depends on the nature of the two surfaces that are interacting with each other and the force pushing those two surfaces together, which in this case we're going to be looking at our normal force. So that's what it's going to be pushing, that's that upward motion that's pushing the surface with that object. So remember, that's also called your support force. So just to give an example of, I guess when we're talking about the two different types of surfaces that we're working with, say if you were to take a curling rock, you were to place it on some ice, and then you were to place another curling rock and put it on some sandpaper. Which one do you think would be a lot easier to push? So the types of materials that you're working with in terms of your surface is going to provide some resistance. So obviously we're going to have less resistance with ice than if we were to have a surface with sandpaper. Okay. So we do have an equation here that relates our frictional force and our normal force. So that is, our frictional force is equal to the Greek letter mu, which stands for coefficient of friction, times your normal force. And so one thing that's going to be really important about your coefficient of friction, that's probably, I guarantee you it's a new term for you. Don't worry, I'm going to give you either a table of values that has your coefficient of friction, or I will just give it to you in your questions, okay? So we're going to continue on with this lesson in the next video. I'm just running short on time. So I'll see you in the next video.